Okay, this is part 2 in the home semiconductor fabrication video series. If you haven't seen the first video already, go ahead and watch that. I talk about semiconductor fabrication basics and all the processes. And then in this video, I'm going to show you around my home chip lab and give you an idea of how you can set up your own and do some of these processes by yourself. And then in the next video, we'll go step by step through making either a diode or a transistor or something like that. So this bench here I have set up with most of my wafer handling and semiconductor fabrication stuff. So these are just some tweezers and stuff. These are wafer tweezers, all stainless steel, and then some plastic Teflon tweezers. This is what I'm using for my spin coating right now. It's far from ideal, but it's a muffin fan from a computer. I clipped all the blades off of it, and then I 3D printed this dish, and then I used this tape to hold my wafer down. And this is a power supply. On the back, I have a little board I made, and that gets this very close to 3,500 RPM, just so I have it somewhat consistent each time. And I have an illuminator set up with the fiber optic cold light coupling thing, so I can see my work. These are just some chemistry things. This is a hot plate, and this is a 3D rotator mixer. These are some wafer pieces. This one here has a 500 angstrom silicon dioxide layer on it. That's why it appears blue. That's used as a field oxide, or 5,000 angstrom rather. That's a field oxide for fabricating field effect devices. These are some other wafers and pieces that I've cleaved up. This is half of a 2-inch wafer here. These are some of the chemicals I used during the process. This is hydrofluoric acid, 2.3%, and about 1% hydrofluoric acid. Using that for etching silicon dioxide. 2 DI water baths, and then some dopants, phosphoric acid solutions, and isopropyl alcohol, and in water, things like that. Have a couple furnaces. That one and the one right there are not quite ideal for diffusion, but I can fit entire wafers without cleaving them up. So these are great for doing oxide growth. So they get up. This one, it gets pretty hot. You just need about 1,000 degrees C to do oxide growth and stuff like that. So like this 2-inch wafer here, I did that oxide growth in this furnace here, and it's got a vent port in the top. I have a thermocouple going in there now, and that's great. I can do nitrogen purges and get temperature readings, and I can make other atmospheres inside of this one. And let's go around. This is a nitrogen tank. Use that during diffusion. It's not completely necessary for proof of concept devices, but it really helps out the electrical characteristics if you can purge nitrogen through the furnace while you're doing diffusion. And then this thing, about the same temperature as the other one, it's just smaller. But I don't have a quartz boat or anything to put the wafers on, so it gets really dirty. And then this is really what you want for diffusion. This is a tube furnace. So there's a quartz tube here. This is a 1-inch diameter. I got this made from a company called Great Glass. There's a few options online, about 35 bucks. And that closes like that. And you can put your wafers in there. You push them with a stainless steel rod, so they're about halfway in the middle. And this thing goes up to 1,400 degrees C. Got this, I think, like 100 bucks or so on eBay. It wasn't bad. So this is great for doing diffusion stuff. It heats up very quickly, and it's it's not the nicest condition. It's got some rust and oxidation on it, but it does the job. Some just like lab supplies and stuff. These are wafer pieces. This is a large 6-inch wafer. It's got a copper layer on it. These are some of the devices that I fabricated. These are diodes, photovoltaics, stuff like that. And then here are some MOSFETs. You can see them. The red little layer in the middle is the gate, and there's 2 like bluish green on either side of it. That's the source and drain. And then there's a substrate connection on the back. I'm just using conductive silver epoxy to make these connections because I don't have a wire bonding machine as of now. And here's the process to make MOSFETs. And that's the process to make diodes or solar cells, planar diodes rather. You can make solar cells by making connection on either side of the wafer as well, but this is a planar setup. You can do it without the silicon dioxide layer if you do the non-planar method. So this is really, on this bench here, is most of what's required to make your own transistors and stuff like that in a home environment. And then over here, some more semiconductor related stuff. There's a curve tracer down there. In that box I have a couple photoresists and their developers. Just assorted chemistry stuff like lab supplies. These bottles are great for storing photoresists in. This is vinyl, like sticky card sign vinyl, and I cut this and I can use it to mask the active areas so I can etch the silicon dioxide layers. So I use this as a mask. Got that on Amazon. Gloves, super important. And up here I have my wafers. So I think this, yes, 25 4-inch N-type wafers. This is an empty carrier. And then these are 25 each, so it's 50 P-type 2-inch wafers here. I've used a few of them. You can pick these up on eBay or surplus places, but all the experiments I've done so far, I've used only 3 wafers so far out of my first 25, and I have a sealed another lot of 25 and then 25 4-inch wafers, so I'm in pretty good shape as far as substrate as of now. I think I showed you guys everything on this bench. This is some ammonium hydroxide. That's good for cleaning things. I use that for preparing surfaces for the photoresist, because when you apply photoresist, you want a completely hydrophobic surface, and you want to do dehydration, baking, and all that good stuff. So when you're preparing stuff for good photoresist adhesion, it's great to use ammonium hydroxide or something like that. You want to stay away from rubbing alcohol. These are some photolithography tests. This is like a copper PCB material, and then this is on a silicon wafer. It says my last name and then Semicon 2016. That was one of the first ones. That's why it looks pretty bad. And I actually exposed that using a DLP projector. So that's a maskless photolithography method, and same with this test pattern here. This test pattern is just in the developed photoresist. It's not actually etched into the copper, as you can see. So that's why the contrast is pretty weak. The line width on this one, there's some other features in there you can't really see. There's the word test on the top of my finger right there, and that's 25. The smallest test is 25 micron line width, and the largest test is 75 micron line width. So pretty big in the scheme of things. And over here, I have thin film deposition stuff, RF source for plasma cleaning and stuff. I'm working on the vacuum chamber. This is a National Instruments USB 6009 DAC I'm using to build a controller for the vacuum chamber. Over here, hot cathode ionization gauge controller, watt meter, resonant quartz thickness meter, so I can get in live time as I'm making films the thickness and rate of those films. And I have Variac to control the thermal evaporation boat. Vacuum stuff, that's a heated vapor trap, Variant Navigator 141 turbo molecular pump, some flanges, and other high vacuum related stuff. A couple microscopes for semiconductor work. That's a Nikon right there, and it's got this awesome readout here that tells me stage movement down to a micron, which is pretty sweet. It's a great scope. And this is a stereo zoom curve tracer, and this is where I keep most of the chemicals, or at least the acids involved with the semiconductor manufacturing. So there's hydrochloric, this is boric acid and phosphoric acid. These are my main dopants here that I use for the semiconductors. Photoresist developer, the hydrofluoric acid I get, of course, from the classic rust stain remover, and some other stuff. Hydrochloric, 37%. Sulfuric acid, I use that for Piranha Clean. This is a potassium nitrate solution, stump remover, and I can use that for anodic oxidation of silicon. And sulfuric acid, I guess I didn't write the content of that, but that's going to be a Piranha Clean, and then RCA Clean parts 1 and 2. Those are in H2O2 solution. And here's the vacuum chamber. So right now I'm getting this ready to do thermal evaporation of aluminum, and I'm going to be using that aluminum to do metallization of wafers, and then I can pattern that with my photolithography setup, which I'll show you in a second, and then I'll be able to make ICs from that. So that's the chamber. Big ISO 500-ish thing on the top, nice big viewport, ISO 200 viewport right here, so I have plenty of viewing angles, which is awesome. Mechanical pump is a rotary vane. It's a Edwards number 12, and then I'm mounting that turbo pump on that 6-inch conflat right there. On this side, valve baritone pressure transducer is going to be a low vacuum gauge. It goes down to 1 torr, or starts at 1 torr rather, and it doesn't really go much below 0.001 torr. And then this is my high vacuum gauge. This is a hot cathode ionization gauge. I have a 4-pin electrical feed through, vent valve, the vacuum. I need to get this flange blocked off here. There's 3 2.75-inch conflats. This is a thermocouple gauge here, and that's going to be my mid vacuum gauge, NPT thread, so I had to make that adapter plate basically. And then this is a 6-inch conflat here. I'm taking that off, and then I'm getting a 90-degree elbow that goes 6-inch conflat to ISO 100, and I'm going to hang my turbomolecular pump, which is over there on that table. I'm going to hang it off right here, and that's going to be backed, of course, with the oil diffusion pump. Down here, there's a UPS power supply. That is an 800 amp rewound microwave oven transformer, and that's attached to these big 1-gauge welding cables that goes into these massive electrical feed-throughs on the bottom, and lets me get that current into the chamber so I can do thermal evaporation, and those are the 2 electrodes coming out in there. That's a thermocouple, that white thing. And then on the bottom here is a controller I'm working on for this stuff, and that's the front of it. There's basically a computer in it and some power supply stuff. It runs LabVIEW, or Windows 7, I have LabVIEW running on it, and then this DAC board is going to go in there, and it's going to read, you know, pressures from my 3 pressure gauges, thermocouple readings, vacuum pressure as well. It's I have 2 mass flow controllers on here, so I'm going to be able to control my atmosphere in this, so I can do plasma cleaning, plasma etching, reactive ion etching, sputtering maybe, you know, all that good stuff. So that's going to be really a lot of fun playing with that. So that's basically all of my home semiconductor setup. I've been accumulating all of this stuff and then all the stuff on that table over there since like October. It's February right now, so still have a long ways to go. This is how I'm patterning my photoresist. It's a not even 720p DLP projector, and it's on this mount so I can point it straight down. I put my substrate with the coated photoresist underneath this here. This is modified optics, so I can focus to a 1/2-inch by 1/2-inch square piece, and then I can focus down with that, a line width about 50 micron, and then if I focus down to a 1/4-inch by 1/4-inch image, I can get down with this projector from 1999, I can get down to 25 micron line width pretty consistently. So that's awesome. With a newer DLP projector, if I wanted to spend a few $1,000s, theoretically I could go past 10 micron feature size, which is awesome for a maskless photolithography method like this. So anyway, that's my semiconductor fabrication setup, and I haven't seen many people online or at all trying to do this kind of stuff, so it'd be really cool if other people wanted to get into this and start making their own diodes and PN junctions, transistors, stuff like that. I'm gonna keep posting YouTube videos as I make progress, trying to make integrated circuits on my YouTube channel here, so stay tuned for that, and keep an eye out for the 3rd video in this series where I attempt to make a transistor. You know, I'm not sure if it'll work. It may work or it may not work, and if it does, that's great. If it doesn't, then we'll have a fun time looking at it and trying to figure out what went wrong with the fabrication of that. So thanks for watching.
You're looking at something so astonishing, it almost contradicts everyday conceptions of reality. It does the work of a room full of electrical circuits, yet it uses almost no energy. Its predecessor cost over $1 million and took up hundreds of square feet, but it costs less than $10 and is smaller than your fingertip. It's called a chip.
Hi, my name's Sam, and in April of 2018, I released details on how I made my first integrated circuit at home. I realized I never mentioned this on my YouTube channel, so here's a quick dive into making computer chips at home. The chips I've made are a simple differential amplifier containing 6 transistors on a 5-micron metal gate PMOS process, which is straight out of the early 1970s. It took me about 2 years to achieve this, but those specs can be improved on quite a lot. The FETs and diodes have really good characteristics, and I've wired it here as a ring oscillator in which 3 NOT gates are chained together to blink an LED. To do this at home, I've had to build and acquire quite a lot of specialized equipment. This is a home-built lithography stepper that projects images in ultraviolet onto the chip from a DLP projector to expose photoresist and pattern the various layers. With parts from eBay and donations, I was able to build a high vacuum chamber, which is for sputtering and thermal evaporation of metal layers onto the chip. I also picked up this electron microscope, which is not strictly necessary for making chips, but makes things a lot easier and was a lot of fun to learn about. This project was great because I got to learn so much about so many different fields. This is a plasma sputtering system in a vacuum chamber that I built, and a number of other plasma cleaning and plasma etching experiments as well. If you want to see more about this, check out my website and YouTube channel. I also had to deal with a number of hazardous chemicals like hydrofluoric acid, phosphoric acid, sulfuric acid, hydrochloric acid, and a number of others. One of the steps involves a very high temperature furnace at about 1200 degrees C for doping. And the final step to put it all together is wire bonding, which I talked about in my last YouTube video, and check that out. And that's it, thanks for watching. My email is on my website, so if you want to share any thoughts or ask some questions, you can contact me there. Thanks.